Welcome to the Problemas channel, Season 2, Episode 4, the episode in which we will discuss the solution of the mathematical problem S2E4. Before we do that, however, please allow me to remind you that I have put together the Season 1 guide, which is a free PDF file that you can find in my GitHub repository. The link to that file and my repository is in the description or the comment section to this video. In this PDF file, I compiled the list of all the episodes that we made for Season 1, and for each such episode, I listed the material that we cover in that episode and the name and the number of the problem that we formulate and solve in that episode. This document, I hope, will make your overall experience and the navigation through the material on this channel much more pleasant. So far, across the episodes in Season 1 and the early episodes in Season 2, we have covered two problem-solving approaches: the transform and conquer problem-solving approach and the reinterpret and conquer problem-solving approach. All the episodes in which we discussed and explained thoroughly and slowly how to apply the transform and conquer problem-solving approach to the process of solving a mathematical problem, I'll put together into the playlist, which is cleverly called Transform and Conquer, and consequently all the relevant episodes in which we explain slowly and thoroughly how to apply the reinterpret and conquer problem-solving approach to the process of finding a solution of a mathematical problem also belong to one and the same cleverly named playlist, Reinterpret and Conquer. You can find all these playlists in the homepage of this channel, and consequently the previous episode, this episode, and if a few several episodes that are about to come will belong to the reverse order playlist, which again you can find in the homepage of this channel. In the previous episode, we solved one mathematical problem using the reverse order problem solving approach, and I explained how that approach works, but because it may seem a little confusing or maybe a little bit too abstract, let me go over the mechanics of the reverse order problem solving approach in more detail one more time. That problem solving approach comes in two main flavors: mechanical and heuristic. Again, these names are mine. If you don't like these names, then be my guest. You're more than welcome to come up with the better names as soon as you understand how this process works. As such, let's say we are given a particular mathematical, let's say, problem, which I will designate with some initial amount of material. This is what's given in the problem. We'll again designate it with letter G for given, and we're asked to, for example, generate a proof or conduct a certain computation or a construction, and this is the material that is sought after. Usually, and pretty much all over the place, what we see in various textbooks is what I refer to as a forward flow of causality. In other words, we start with what is given, and then through a series or through a chain of if P then Q implications, we somehow zigzag our way into what is sought after. For example, let's say we depict one if P then Q implication with a geometric point. Consequently, this forward flow of causality can be represented, for example, with one implication, another one, another one, another one, and another one. And the flow of causality, if this is true, then this follows, and if this is true, then that follows, and so on, we will represent with an arrow like so. And then usually when we craft a forward flow of causality argument, we zig and zag our way through such implications, and because each and every solution is a finite description of a finite number of steps, where the word step really represents an if P then Q implication, then sooner or later, or inevitably, there will be logically the last implication, the consequent of which will be what is sought after. In other words, in a forward flow of causality reasoning, we begin with what is given and we end or terminate our chain of reasoning or chain of implications with what is sought after. However, sometimes it is quite difficult and quite challenging to craft precisely that chain of implications to which we refer a solution of a problem, at which point we look for different ways to help us generate that solution. And in some sense, all the problem-solving approaches that we studied so far, they transform and conquer and reinterpret and conquer, the problem-solving approach that we're studying now, reverse order, and several more problem-solving approaches that we will study soon, they all act as helpers or as stepping stones that may allow us to precisely generate this flow of causality where we begin with what is given and we terminate or end with what is sought after. The reverse order problem-solving approach prescribes that instead of starting with what is given and terminating with what is sought after, we begin precisely with the state of or with material that is sought after. Again, at this point, we make one big assumption that a given problem does have a solution, and that is why we think and act like a mathematician, and we wrap our description of the reverse order problem-solving approach into the language of if. If a given problem does possess a solution, then we begin with that solution, with the sought after material, and temporarily we ignore precisely how that sought after material was obtained. For all we care, we can, for example, pretend that an all-knowing mathematical oracle somehow put this solution together and handed it to us, omitting all the intermediate steps. And the whole purpose of that maneuver is to help us glean the insight into a way of constructing this forward flow of reasoning. And as the reverse order problem-solving approach prescribes, we begin with what is sought after, and then we try to reason our way towards what is given, towards the material that is given. For example, again, we represent these implications with, for example, yellow for distinctiveness, with yellow points. We manage, for example, we start with material that is sought after. Then we make the first step or the first implication. If this is true, if what is sought after is true, then this and that must be true. And then this and that must be true. This and that must be true. This and that must be true. Maybe we can construct that flow of reasoning that goes in the opposite or reverse order direction. Somehow we zigzag our way in reverse order like so and arrive at what is given. And the whole idea of that maneuver is to generate hints or insights or actionable tactical material that will allow us to construct the forward flowing chain of reasoning. And again, because these implications will be different, we will designate them, let's say, with red points. So it may so happen, it's not guaranteed, there are no guarantees of any kind in this process, but it may so happen that after we craft a reverse order or a reverse timeline flow of reasoning that begins with what is sought after and terminates with what is given, we may be able to flip that line of reasoning and generate a normal or traditional usual forward flow of causality. For example, we can say, aha, if this is true, then, for example, this will be true, and this will be true, and this will be true, this will be true, this will be true, and we may succeed at generating the actual line of reasoning that is sought after in the usual way that in which it's presented in all the textbooks. And the way these things go, if we omit the details of the devil's kitchen, so to speak, when we're not privy to how the forward flow of causality was generated, because we hide the path over which we got to this line of reasoning, then it can be, and usually does sound, very mysterious. Where did it come from? The two flavors of the reverse order problem solving approach, mechanical and heuristic, pretty much operate in the same way, except that the mechanical flavor of the reverse order problem solving approach is quite suitable for computational problems in which certain process stage by stage or step by step unfolds. And the mechanical flavor of the reverse order problem solving approach prescribes that instead of beginning at the first stage or first step of such a process, we begin with the last step or the last stage of the process that is described in the problem and try to trace our steps backwards towards the material that is given. And again, this whole idea, as a loose and vague analogy, may come from the act of, for example, taking a movie camera and recording the movie of the process that unfolds in a given problem, as we saw in the previous episodes when we had a set of swans landing over a set of lakes. Then normally we watch the movie from the first frame towards the last frame, but in both of these flavors of the reverse order problem solving approach, what we do is, instead of rewinding the movie after we shoot it, we actually start watching that movie from the last frame to the previous frame, to the previous frame, previous frame, and so on, until we arrive at the very first frame. Now let us end again. The heuristic flavor of the reverse order problem solving approach can apply obviously to computational problems, which because it's slightly more generic, but it also works with non-computational problems. And admittedly, sometimes for us to apply the heuristic flavor of the reverse order problem solving approach to this or that problem will require quite a bit of powers of perspicacity, and we will look at such problems. But across these two flavors, the mechanical flavor is slightly more straightforward, slightly more easier to understand. That is why we begin our discussion of the reverse order problem solving approach with the mechanical flavor, just to get the idea of how that problem solving approach can be applied to the process of finding a solution of a mathematical problem. Now let us see how this process, how this little bit of theory can be applied to the mathematical problem S2E4, in which the devil spotted a loiterer, or a guy who was hanging out doing absolutely nothing useful. The devil approached this guy and said, listen, every time you cross this bridge from here to here in any direction, or from here to here, the amount of money in your pocket will triple, will grow by 3 times as shown over here. And the deal is that after each crossing and the amount of money multiplying by 3, the devil requested that he gets his cut of $27. The way it goes, the loiterer agreed to this deal. He crossed the bridge 3 times. From here, let's say 1, from here to here 2, from here to here back 3, and after the 3rd crossing, the loiterer was left with no money in his pocket. And the question is, How much money did the loiterer have at the beginning of this bargain before he agreed to this deal? Again, quite often the problems of this type can be solved in a traditional or forward flow of causality, but the solution may not require much intellectual effort, but the mechanics of obtaining the solution are quite horrible, convoluted, and quite often error prone, meaning that even though the task that we set for ourselves in the forward flow of causality solving of this problem may be straightforward, but it is more than easy to make a mistake with this approach. And again, quite often, if we begin solving this problem in reverse order or from the final state of matters in the local problem, then the solution can be obtained in a less error-prone fashion and more straightforward way. So in this case, let's first try to solve this problem in reverse order. And as the mechanical flavor of the reverse order problem solving approach prescribes, because here we have a very well expressed process, three-stage process, we can depict these processes, for example, schematically like this. Let's say the loiterer started from here, from that side of the bridge, and then we will designate this as our first crossing in this direction, let's say. Then after the first crossing, with this point, we will designate the first cut is given to the devil. Then, right after that, the second stage happens, and the loiterer crosses the bridge for the second time in this direction, let's say. So it will be second crossing. And after the loiterer crosses the bridge for the second time, with the point right here, we'll designate the second cut that is given to the devil. And right after that, the loiterer crosses the bridge for the third and the final time in this direction. We'll designate it with the third crossing. And with this point right here, we will designate the third, and the final cut that is given to the devil. So far so good. So this should be a straightforward arrangement. First crossing, first cut given, second crossing, second cut given, third crossing, third cut given. So far so good. Now, as the mechanical flavor of the reverse order problem solving approach prescribes, instead of starting our solution with the first stage or initial state of the process, we start the search for a solution or search for an answer in the problem with the very last state of affairs. And what is the last state of affairs over here? Well, this state of affairs means that the loiterer has precisely $0 in his pocket, because once he gave the third cut to the devil, there is no money left, as is given to us by the problem statement. Here, let's say we again recorded this process of loiterer crossing the bridge and giving cuts to the devil with the movie camera, and now we, without rewinding the movie, start watching that movie in reverse order, starting from the last frame and moving towards the first frame. What would we see? Well, after loiterer gave the third cut to the devil and had no money left in the pocket in the forward flow of time, if we watch that movie in reverse order from the last frame towards the first frame, what will we see? Well, it will look kind of funny, but the loiterer will put the money into his pocket, right? He will put the money, instead of giving the money to the devil in the forward flow of time, in reverse order. It will look like he's putting money in his pocket. So when we give money to someone, we reflect that process with the operation of subtraction. But if we receive money, then we reflect that fact with the arithmetic operation of addition. So if we watch that movie in reverse order, what will we see? Loiterer puts the money into his pocket, which means that we reflect that with the arithmetic operation of addition. The cut of the devil, we know $27, so 27 will be the amount of money that the loiterer has in his pocket immediately after he put the money in his pocket in reverse order. And what does that also mean? That also means that $27 will be the amount of money that the loiterer has precisely after crossing the bridge for the third time. So at this point right here, the loiterer has $27 in his pocket. If we watch that movie in reverse order, what will we see starting from this segment of the movie? Well, at this point, we will see that in a funny way, the loiterer walks across the bridge in the opposite direction. So he will wind up over here. And if in forward flow of time, the devil triples the money that the loiterer has when he crosses the bridge walking forward, it means that in reverse order, when we watch this movie in the opposite direction, unfolding in the opposite direction, what will happen to the amount of money that the loiterer has in his pocket? Precisely, instead of increasing, here the amount of money in his pocket will decrease. So 27 divided by 3 will be what? 27 over 3 is 9. So at this stage over here, the loiterer will have exactly $9 in his pocket. And if we keep watching that movie, what does that mean? It means that $9 is the amount of money in the loiterer's pocket immediately after he gave the second cut to the devil. The cut is $27, so if we watch that movie in reverse order, instead of giving the second cut to the devil, the loiterer in a funny way will put the money into his pocket. So here 29 plus 7 will be what? 36. We'll write it over here, 36. $36 here will be amount of money in forward flow of time immediately before the loiterer gives the second cut to the devil, and immediately after he crosses the bridge for the second time. But remember, we're watching this movie in reverse order from the last frame towards the first frame. So what we will see at this point if we watch the movie in the reverse order? Again, it will look funny, but the loiterer will walk backwards across the bridge, and the amount of money in his pocket will what? Instead of increasing by 3, we'll have to apply the inverse operation. The amount of money in his pocket must decrease by 3. So 36 divided by 3 is 12. So we write down $12. $12 is the amount of money in the loiterer's pocket. In which state? In the state immediately before crossing the bridge for the second time in the forward flow of time, or immediately after the loiterer gave the first cut to the devil. Because we're watching this movie in reverse order, instead of giving money to the devil, the loiterer, in a funny way, puts the money into his pocket. So if we put the loiterer into this stage immediately before giving the first cut to the devil, what we will see? Instead of subtraction, we'll use addition. 12 plus 27 will be what? 39. So $39 will be the amount of money in the loiterer's pocket immediately before he gives the first cut to the devil, and immediately after the first time he crossed the bridge. Now, as the reverse order problem solving approach prescribes, we keep doing the same thing. We keep moving backwards through time by, technically speaking, watching that movie from the last frame towards the first frame. And when we watch that last segment of this movie, last several frames, what we will see? Again, we'll see that loiterer is walking funny in the opposite direction, and as he crosses the bridge in the opposite direction, what will happen to the amount of money in his pocket? Well, again, if in forward flow of time the amount of money increases when the loiterer crosses the bridge, then in reverse order the amount of money will decrease by how much? By the same factor of 3. 39 over 3 is $13. And this is the answer to this problem. The loiterer had $13 in his pocket before he agreed with the deal that was offered by the devil. Apparently, our loiterer was not aware of the reverse order problem solving approach, because if he were aware, he probably would not agree to this deal, because in just 3 crossings he was left with no money in his pocket. One more time, as a general overview, how did we obtain the answer to this problem? We obtain the answer to this problem by applying the mechanical flavor of the reverse order problem solving approach, which prescribed that instead of looking or generating a solution of the problem starting from what is given and winding up with what is sought after in the last stage, we switched things around and we started for our search for a solution from the very last state, or from the very last stage of this process, and we worked our way backwards or in reverse order. And instead of multiplying and subtracting, what did we do? We did addition and division. So far so good. Instead of multiplying and subtracting for giving cut, we used addition and division on every step backwards through these stages, and that is how we obtained the answer to this problem. If this is understood, let us try to solve this problem now in the normal flow of causality. And by the way, this is also a way to double check or verify our solution. For example, if I claim that the loiterer had $13 in his pocket before he agreed on the deal with the devil, how do we verify my claim? Well, we now play out or watch that movie unfolding in the traditional forward flow of time, and we say, okay, he had $13 before the first crossing. After he crossed the bridge for the first time, 13 times 3 is 39. He had $39 in his pocket, which means that the devil had somehow to do what? Had to put $26 into the loiterer's pocket. Then, after the first cut, 39 minus 27 is 12. So right before the first crossing, the loiterer must have $12 in his pocket. Crossing the bridge for the second time, 12 times 3, this time we multiply 36. The loiterer gives the second cut to the devil. 36 minus 27 is 9. He has $9. The loiterer has $9 in his pocket before the third crossing. After the third crossing, we multiply the amount of money in the loiterer's pocket. 9 times 3 is 27, and bingo, this is the amount of money the devil collects on every bridge crossing in return for tripling the money in the loiterer's pocket. And it happens to be exactly the devil's cut. 27 minus 27 this time is $0 in the pocket. Consequently, if we do not know what that number is, we'll say, okay, this number is, for example, X. X is the number, is the amount of dollars in the loiterer's pocket before the first bridge crossing. After the first bridge crossing, the loiterer will have 3 times X, and after the first cut is collected by the devil, he will have minus $27 in his pocket. Now, during the second crossing, the amount of money in the devil's pocket will what? Triple. So again, 3 times this guy. And then here, the devil collects the second cut, minus 27. Minus 27. This 2 parentheses here reflect this stage of our problem. After the third after the third crossing of the bridge, the amount of money in the loiterer's pocket triples, so this parenthesis multiplied by 3. 27 is subtracted for the third and the final cut, minus 27. And we're told that at this stage of the problem, the loiterer has nothing left in his pocket, $0 are left. But again, we understand that I've constructed 3 crossing just for demonstration purposes, and for a cheap thrill, I came up with the number 13. You can change the numbers. Once you understand how these things work, you can change the numbers any which way you like. 13 in at least Western civilization is the devil's dozen. That's why I picked 13. But here at this stage, we terminate in our process, which means that we constructed our equation in the forward flow of causality. And if we wanted to make this problem even more difficult, we would add more crossings, which means that the equation that we constructed over here will be even more and more convoluted, more and more cumbersome. But in this case, okay, we terminate with the equality to 0. Now we solve this equation. Move 27 over here, 3 and 27 subtract. It means that this parenthesis here, 3x minus 27 minus 27 equals to what? 3 and 27 comes out to 9. This is 9. That means we move 27 over here. We get what? 3 times 3x minus 27 equals 9 and 27 is what? 36. 3 and 36 agreeably cancel out, and we get what? 3 minus 27 equals 12. 36 over 3 is 12. Again, we move 27 to the other side here. We get 3 times x equals what? 37, 39. 39, and this on the final stage, we see that 39 over 3, x is $13. So this is the answer to this problem. The loiterer had $13 in his pocket before he agreed with the deal with the devil, and that is the solution that we obtained in the normal or traditional forward flow of causality. Here, as a matter of fact, one of the other reasons why I picked this specific problem is because we can see that some people may argue, well, Roman, look, here your reverse order business is not really that clear that we win a lot in comparison with the forward flow of causality. Sometimes it is the case, yes. It may so happen that solving the problem in reverse order may not afford maybe that much advantage, but still, this is how mathematics works. And just to understand how the mechanical flavor of the reverse order problem solving approach works, we pick this problem, and it's a good idea to compare both the reverse order solution and the forward or traditional flow of causality solution. Once you understand, again, we go back to the wisdom of the reinterpret and conquer problem solving approach. We understand that each and every mathematical problem consists of two parts or two big pieces. One piece that does not change and represents the technical essence of the problem. The other part is the material that does change and thus represents the irrelevant minutia in this case. And once we see through what is what and understand what is the irrelevant minutia and can be ignored and what is the technical essence and what must be concentrated on, we can wrap the technical essence of the problem into all sorts of different languages. By the looks of it, in this case, what is the technical essence of this problem? Multiply by 3, subtract 27. Again, I picked these numbers for a cheap thrill of getting the devil's dozen and the answer 13. You can pick any numbers. For example, a times x plus minus b is a straightforward looking expression that can be wrapped into all sorts of vocabulary with all sorts of words, and a problem can be constructed. And as a matter of fact, we suggest that this is what you try to do on your own. Try to pick, for example, different numbers instead of 327, pick some other numbers, 5 and 19 or whatever else, and try to construct an interesting mathematical problem that again can be solved in a straightforward manner in reverse order. I'll give you another example. This will be an informal problem, but think about it. Let's say we have two trees. We have two trees. We'll designate this left tree, and this will be T sub r for the right tree. We have X birds sitting on the left tree and Y birds sitting on the right tree. And then on schedule, on the clock, your favorite amount of time, every second, every minute, every hour, doesn't matter, every amount of time, one and the same process unfolds. One half of the birds that sit on the left tree fly over to the right tree. For example, once, left to right, half of the birds that sit on the left tree fly onto the right tree. And then one half of the total amount of birds that sit on the right tree, they fly back to the left tree. And then again, given a chosen unit of time, one half of all the birds that sit on the left tree, they fly back to the right tree right here. At that time, we take a picture of the situation that unfolded here, and then we see that on the left tree, for example, there are 11 birds, and on the right tree there are 19 birds. Question: how many birds were on each tree before they started jumping around back and forth? Again, this problem of course can be solved in the forward flow of causality. For example, after the first jump, we will have what? There will be x over 2 birds on the left tree and y plus x over 2 birds on the right tree. Then half of these birds will jump over here, half will be left, and so on. If we construct probably, what is it? There will be two equations which will be quite ugly with all these fractions. One is equal to 11, the other equal to 19. Unfold all this horrible fractional number arithmetic, and then we should arrive at the answer. With these numbers, actually this should be 28 and this should be 2. I will not be explaining exactly how this works. This will be an informal homework assignment for you guys. Try to explain how these numbers can be achieved in reverse order, and also then double check and see how this problem can be solved in a forward flow of causality. This is it for this segment, and now we will move on to the next several challenges. In our next episode, which I titled Apples of Discord, we will discuss the solutions of three mathematical problems: the problem S2M5, the problem S2M6, and the problem S2M7. All these three problems can, of course, be solved by other means, but because right now we're in the middle of studying the mechanics of the reverse order problem solving approach, as a gentle hint, uh, these two problems, S2M5 and S2M6, as it will be evident pretty soon, can be solved by applying the mechanical flavor of the reverse order problem solving approach to the process of solving these problems. And the problem S2M7 is slightly more sophisticated, so to speak, slightly more difficult, and a solution of this problem can be unlocked in a reasonably straightforward manner if we apply to the process of searching for that solution the heuristic flavor of the reverse order problem solving approach. In the problem S2M5, we're given the following setup. Once upon a time, there lived a poor peasant who once managed to get into the king's palace, and the king said, make a wish, what do you want? The peasant knew about this garden of apples that was sitting behind three fences, and wonderful magic golden apples grew in that garden. The peasant said, I want to get as many apples from this magical garden as I want. The king said, yeah, sure, go ahead. But when the peasant approached the garden, the way things work in real life, the guard who was watching the first gates attached to the first fence said, listen, when you walk back, I want 1/2 of all the apples that you will be carrying at that point. The peasant agreed. He stepped up to the second gate, and the guard who was watching the second gates attached to the second fence said, I want the half of all the apples with which you will approach my gate. The peasant said, yes, of course, why not? The peasant walked through the second gate and approached the third one, and he said, may I enter? The guard said, yes, sure, but when you come out, I want 1/2 of all the apples that you will be carrying. The peasant agreed, and by the time the peasant collected as many apples as he could carry, he walked through the third gate, second gate, first gate. By the time he came out and gave all the shares that he agreed to give to all the guards, he had 20 apples on him. And the question is, how many apples did the peasant collect in the garden to begin with? That is the problem S2M5. In the problem S2M6, we will also be dealing with apples. And in that problem, we have the following process unfolding. At the beginning, X is the unknown number of apples were put in a row as shown here with these points. An apple, an apple, an apple, blah, 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 so on, the apple. Then between every two immediately adjacent apples, for example, between this apple and this apple, between this apple and this apple, this apple and this apple, someone adds two more apples as shown. These apples are depicted here in white. The inserted apples are depicted in yellow, so between every two adjacent apples, two more apples are added. And once a new string of apples is formed, as depicted over here, on the second iteration, the same thing happens, but between every pair of adjacent apples, three more new apples are inserted. Three more apples are inserted between the first and the second apple here. Three more apples are inserted between the second and the third apple. Three more apples between this apple and this apple, and so on. And by the time we line up all the apples after that maneuver, it turns out that we have 97 apples. The question is, how many apples were lined up on the table originally? That is the mathematics problem S2M6. The mathematics problem S2M7 is a little bit different with respect to all the problems that we looked at so far. This is a problem that seems to be on the elementary Euclidean geometry. And in this problem, we're given a square. A, B, C, D is a square. So let me probably let you guys know that A, B, C, D is a square. And inside that square, a point E is picked in such a way that the triangle AEB is isosceles, and the interior angles, let's designate this with these three guys, the magnitude of the interior angles at the base of this isosceles triangle is 15 degrees. 15 degrees for the magnitude of the interior angle BAE, and 15 degrees for the magnitude of the interior angle EBA or ABE. Under these conditions, the challenge is to show that the triangle shown here with red, the triangle DEC is equilateral. In other words, as shown over here, the distances between the points D and C, C and E and E and D are all the same. Let's say the length of this, the length of the side of each square is A. Doesn't matter. So here we have A. So apparently, and this is the challenge to show that the triangle DCE or DEC is equilateral. Sometimes on Quora and off Quora, I'm asked, Roman, where do these problem-solving approaches come from? This is actually a very interesting question, and some of the problem-solving approaches, such as, for example, divide and conquer, are popular and well studied not only in mathematics, but, for example, in the computer science, when, for example, we search various search or sort various structures, such as a linked list, for example, or an array. But consequently, some of these problem-solving approaches live, so to speak, on the great international mathematical grapevine, and they're known under well-advertised names in various countries that care to study these problem-solving approaches. But some of these problem-solving approaches can actually be found by you. This is what I sometimes do, and the source for the discovery or for the search and finding of these problem-solving approaches pretty much I described in season 1 episode 2, where we explain how to practice mathematics correctly. And in our view, that version of practicing mathematics correctly amounts to following a 4-stage process. In the first stage, we try to understand problem statement thoroughly, deeply, and correctly, because unfortunately, many times students jump into solving the problem without really understanding what exactly is required of them, and they do sometimes come up with an answer, but that's an answer to something else, not at the problem given. So at the first stage, we spend as much time as needed to understand what is exactly required of us in this specific problem. In the second stage, to which we move on only after the first stage is complete and we understand what we need to do, we stir our creative juices and we generate a solution. We generate a solution of a problem at hand. And again, a lot of times, that is the stage where many students of mathematics bail out, so to speak. They solve the problem and they move on and do something else. Again, that's their right. We live in a free universe. Why not? What I do, however, is I move on to the third stage where I reflect on my problem-solving experience, reflect on the problem-solving experience, and analyze the points where, for example, I got stuck. Did I get stuck because I did not know or forgot about a specific theorem? If the answer to the question is yes, that means that I need to go hit the books and study theory deeper. If I missed this or that tactical maneuver that allowed me to solve this problem, then I analyze the context and commit to memory this specific situation where this maneuver was applied. So the next time, hopefully, I will be able to apply that maneuver in similar context. And that is also one of the keys for the next step. In the fourth and final stage, it is a good idea to try to generalize the solution of the problem. For example, if we solved a two-space problem, can we solve a similar problem in three-space, four-space, five-space, and n-space altogether, just as an example? And after we succeed, for example, at generalizing the solution of the problem, the final step is try to abstract the solution of the problem. That is where the actual material for the discovery, if you will, of the problem-solving approach is sitting, because the abstraction of a solution can be defined in which way. For example, it's a process where we separate the local jargon, the highly specific terms, and replace them with a generic description. And amazingly enough, the way things work in mathematics is that generic description of how generic and concise short description of how this problem was solved becomes, in some sense, a description of the corresponding problem-solving approach. And the amazing part about how mathematics works is that we may come across this generic or jargon-free, mathematical jargon-free description of how this problem was solved in one vaguely defined layer of mathematics. And then when we export that generic template described in, let's say, plain spoken English, as we did so far over here, amazingly enough, that generic description, that template, that problem-solving approach may either fail spectacularly. Why not? Failure is always an option in this endeavor, in this business. But sometimes these generic templates, these simple descriptions, work amazingly well in different layers of mathematics. Consequently, when you try to solve these problems, S2M5, S2M6, and S2M7, using the reverse order problem solving approach, again, the first two of these problems can be solved using the mechanical flavor of the reverse order problem solving approach, and the third problem can be solved by applying the heuristic flavor of the reverse order problem solving approach. The application of these approaches to the process of unlocking a solution of the problem does require us to think at a little bit of higher or extra level of abstract cognition, but the time and the effort invested into the struggle with understanding how this works will pay off in the future when more serious, or let's say college level mathematics is taken on. This is it for this episode. Thank you very much for your time. Thank you for watching. I'll see you in the next episode, in which I will discuss the solutions of the problems S2M5, S2M6, and S2M7.